Hello. So I thought I would just post a video from a physics problem that I thought was kind of interesting. Um, so I already have, I drew the setup there, and what we're looking for is the angle theta. And the original problem had these as pool balls. So if that helps the imagination, you have a pool ball of the cue ball of mass m hitting another pool ball of mass m, and after it's not hit directly in the center, it's hit off to the side a little bit so that the cue ball flies off in an angle, and the pool ball, the numbered ball, also flies off at an angle. So if you imagine that the velocity vector here from my cue ball, which is labeled velocity initial, so that velocity vector going from the cue ball to the numbered ball, it is perfectly horizontal. It's not in my picture, so just imagine that's like along the x-axis. Then we want the angle between the velocity vector of the 9 ball with the x-axis. So that's what we're looking for. And to solve this, and then a couple of constraints were given. So it's perfectly elastic. We can ignore friction and ignore the spinning of the balls, because really in pool, if you, depending on where you hit the cue ball, what position on the cue ball, it may put a spin on the cue ball, which would change everything in the problem. But let's imagine that there's no spin that would interfere with this interaction. So so the first thing, it's perfectly elastic, so that means the both momentum and energy are conserved. So let's see, where do I want to write this at? Maybe right below it. So we have momentum initial equals momentum final. And for energy, in this case we're concerned with kinetic energy. Kinetic energy equals kinetic energy final. Notice that this energy is a scalar quantity, whereas momentum is a vector quantity. So what we have then is the and the masses of the balls are the same. So we have mass times velocity initial as a vector plus, well, it would be mass times the velocity of the 9 ball, which the initial velocity there is 0, so actually we can say plus 0 equals the mass of the cue ball times velocity final as a vector. That's meant to represent the velocity vector of the cue ball, plus the mass of the numbered ball times the velocity vector of the number ball, which in this case is supposed to be a 9, the way the problem was set up, the 9 ball. So that's what we have for momentum. For energy, we just have, we'll have the same thing here, because where the kinetic energy of the 9 ball goes to is 0, because the velocity is 0. So we're going to have 1/2 mass times velocity initial squared as a scalar quantity plus 0 equals 1/2 mass times velocity final squared plus 1/2 mass times the velocity of the 9 ball squared. Now we're going to have to split up this these velocity vectors into their component parts, and it's not really a good place to write it. So if I were to imagine that this axis, this direction, x-axis, and going in this direction is the y-axis. Except I would probably put the origin on the cue ball, but I didn't want to draw over the cue ball, so we're going to have mass times velocity initial x equals mass times velocity final x plus mass times velocity the 9 ball x. And yeah, I'm gonna this one's already done. We're gonna keep this as it is. So I'll move the y direction for the momentum right beside this here. Mass of the velocity initial in the y direction equals mass of the velocity final in the y direction plus mass of the velocity of the 9 ball in the y direction. So now we just need to figure out some what the x and the y components are, like as a number value. So we have, let's see, where do I want to go next? Yeah, so in the x direction here, like if I were to take, it's kind of hard to redraw over everything. If I were to take this right here, so that this point is our 9 ball, this is velocity 9, and this is our horizontal. This would be the vertical axis. That's a right angle. So for the velocity vector of the 9 ball, this is velocity 9y, this is velocity 9x, and our angle, theta, right here. And so in this case we have velocity 9x, so that would be adjacent. So so that's going to be cosine. So we would have, where to write that? Cosine of theta equals adjacent, which is v9x, over top of hypotenuse, which is v9. So then we multiply both sides by v9 and we get v9 cosine of theta equals velocity 9x. And now that we can plug in for velocity 9x, and we can do the same process for v9y, except it's going to be sine of theta. It's going to be v9 sine of theta equals v9y. And on the other side, for velocity final, we can do the same thing. And actually, there's something I missed in the setup of the problem. This angle was also theta. That was given in the problem, and I forgot to write it down. So so we'll end up with the same things on the other side. And as far as velocity initial, the velocity vector of the cue ball, we have it's all in the x direction and none of it is in the y direction. So when we're dealing with x, we'll have I think you can cancel those out, can't you? Yeah, and because the masses are the same, you can cancel out all the masses. So if you were to, like in this left-hand equation, for the x components of the momentum vectors, then if you divide every term on each side by the masses all cancel out. And the same is true in the y direction. So we're going to have velocity initial x, which is just velocity initial, equals velocity final x, which is going to be v final cosine of theta plus v9 of x, which is going to be v9 cosine of theta. We do the same thing for the y direction, the y components, and velocity initial y in this case will be 0 because there is no velocity in the y direction of the cue ball, equals velocity final sine of theta plus velocity 9 sine of theta. So now we have these three sets of equations, and if we put these together, we can solve for theta and get an equation for theta, or perhaps we'll get lucky and get a value for theta. So let's see. I could randomly start throwing things around, but I want to try to do it the same way that I did during homework. So let's take the kinetic energy equation, which actually in this one I should have canceled these out. So again, if we divide every term, well, if we multiply every term by 2, all the 1/2s cancel. And if we divide every term by m, then all of the m's cancel. And I'm going to take this equation for kinetic energy. So rewrite it up here, kinetic energy. But we're going to solve for V9. And I don't think I need to do all of that. I think it's pretty easy to do. So V9 is going to equal, we have V initial squared, and we have V final squared on the other side, so we're going to subtract it to get it to this side of the equation, V final squared. And we had originally V9 squared, so we're going to have to take the square root of both sides. So that's, we solved the kinetic energy for V9. Then I think the next best thing, we'll take V initial and we'll solve for cosine of theta. So in this one, I'll rewrite the whole thing. So this would be momentum x, and we're going to take, we have V initial equals V final cosine theta plus V9 cosine of theta. We can factor out cosine of theta, so we get V initial equals cosine of theta times V final plus V initial. And then we can divide by V final plus V initial, and we'll get cosine of theta equals V initial divided by V final plus V initial. So now we have solved for cosine of theta from the x components of the momentum vector. And then we're going to take the y components of the momentum vectors, and I think we want to solve for velocity initial. If that's one second in my notes here. No, we're going to solve that for v9. Yeah, so we have momentum in the y direction, and this is 0 equals velocity final sine of theta plus v9 sine of theta, and looks like the first thing that we should do is factor out the sine of theta, and then when we factor it out, we can take 0 divided by sine of theta, and that's still 0. So we can have 0 equals velocity final plus velocity 9. And then let's keep v9 as positive, so we'll subtract the v final and get it to the other side. So v9 equals negative v final. Yeah. Okay, so we have these three equations, and when we take, what was the first thing I did here? Oh, you know what? I made a mistake here. I made it the first time I did it, and I made it the second time I did it. So in the y direction, this is actually velocity final sine of theta minus v9 sine of theta, and the reason is because the way I set up the axes, v9, the velocity vector, is going in the negative direction, the negative y direction, whereas v velocity final is going in the positive y direction. So this was negative here, which means this was negative here, this was negative here, and this was positive here. So v9 equals v final. Yeah. So we have these three equations now. v9 equals the square root of velocity initial squared minus velocity final squared. v9 equals v final cosine of theta equals velocity initial over velocity final plus velocity initial. And we want to take this is the one I did first up here, I think. Yeah, so first let's take let's start with, I get that for velocity initial, v9. Oh, you know what? I wanted to solve the kinetic energy for velocity initial. So it's almost the same thing, but it's going to be velocity initial equals the square root of, make sure I'm doing everything correct here, velocity initial equals the square root of velocity final squared plus v9 squared. Final squared plus v9 squared. So now we should be able to plug in velocity final. We could plug in either one, v9 or v final. The way I did it before was to plug in v final for v9. So let's do that. So we have velocity. Let's see, those are kind of our starting equations. We have velocity initial equals the square root of velocity final squared plus, I'll just rewrite it again, velocity 9 squared. But we're going to plug in velocity final for velocity 9. So we get velocity initial equals the square root of velocity final squared plus velocity final squared, which is going to be 2 velocity final. And then when we take the square root, we're going to get square root of 2 times velocity final squared. And since they're multiplied by each other, we can take the square root of each individually. So we're going to have velocity initial equals square root of 2 times velocity final. So that's going to be very helpful. And then I think I did the same thing for, let's see, no, that's velocity initial cosine of theta. I think this is where I went next. So I took this cosine of theta. Whoops, I wrote cotheta. Cosine of theta equals velocity initial over velocity final plus velocity initial. So we have, what did I do there? Velocity final minus, that should be minus velocity initial. One second. Velocity initial over velocity final minus velocity initial. Why is it minus? Velocity. No, it's a plus sign. I wrote it wrong in my notes. Okay, so cosine of theta. This right here should be a velocity of 9. That's really sloppy. So I will just rewrite it. We have cosine of theta equals velocity initial over top of velocity final plus velocity of the 9 ball. And I'm gonna run out of room unless I'll write it straight below it. So then we have cosine of theta equals velocity initial over velocity final plus velocity final. We can plug that in because we found earlier that velocity of the 9 ball equals the velocity final. Then we're going to have cosine of theta equals velocity initial over 2 velocity final. And velocity initial we found right here. So we're going to have cosine of theta equals square root of 2 velocity final over 2 velocity final. Both velocity finals cancel, which is really nice because now we don't have any variables left except for theta. And I'm also going to take the inverse cosine of both sides, so we'll get theta equals inverse cosine of square root of 2 over 2. And due to our little diagram that we drew and just knowing how pool balls bounce into each other, we know that this has to be 90 degrees or less. So theta equals, and if we were to do our unit circle, this is in radians. Do it down here. So we have our unit circle, and if we have the square root of 2 is somewhere between 1 and 2. So if we had square root of 2, 2, well, maybe it should be more over there. And cosine is the x component, square root of 2 over 2. And if you have this memorized, the y component at this location on the unit circle is square root of 2 over 2 as well. And the angle here is 45 degrees. If you didn't know it, sorry, I said it's in radians. It's not in radians. It's not in radians, or it's a value. It's a x component. So this was 45 degrees. I mean, you could also say in radians, which normally you would do on a unit circle. So if it were radians, it would be pi over 4. That's not very helpful to normal people who use degrees in everyday language and usage. So theta here, both of our angles that we originally wanted to find are 45 degrees. And the things that we were dependent on is it should be, yeah, the fact that both angles were the same allowed us to do a lot of that canceling. So if we had different angles, it wouldn't have worked out quite the same. The fact that both of our masses of our objects were the same allowed us to do a lot of our canceling. So if our masses were different, then the process would have been a little different. What else? The given information, the fact that it was perfectly elastic, that we could ignore friction and ignore the spinning of the balls, all of those things came into play. But with all of those things being true, then the angles here have to both be 45 degrees.